is at the top of this page. Proving mechanism by product regiochemistry. If you look at this reaction, we have an alkyl bromide. We're reacting with ethanol. The delta sign implies heat. First off, this is a solvolysis reaction. Solvolysis, ethanol is usually a kind of a typical solvent. Basically, the alkyl bromide is reacting with the ethanol solvent. Two products formed, two regioisomers. The bromine has been substituted. The bromine was a leaving group. We have the O-ethyl now in place of the bromine, but if you look at it, O-ethyl replaced bromine, but over here, how did the O-ethyl get on that carbon? What was that? Well, let's look at it. Ethanol, heat. Let's show a mechanism for forming both of these products. What's the first step? What do you want to do first?
Ionization.
Ionization, yes. Very good. This just ionizes off. This becomes what? Carbocation plus Br minus. Leaving group can just leave. Just like it leaves HBr, we put HBr in water. We'll ionize and leave the H. Here it's leaving carbon. Takes a little heat to do this. Maybe, maybe not. What type of cation did we form? Secondary. Secondaries are doable. Don't form a primary carbocation ever. That's not good unless you absolutely have to. In terms of proposing a mechanism. Secondary is doable. If this was tertiary, it'd be even easier to do this. Might be able to do it in a SEP funnel, shaking them a little bit. A little bit of heat to get this to ionize. Okay. What's next? How might we get this product here?
Inversion.
The oxygen attacks the carbocation.
These electrons attack here. Can ethanol be a nucleophile? Sure, it has a lone pair. What does this give? Boom, 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 boom. We now have bond to oxygen. There's an ethyl and there's an H. There's a lone pair. Other lone pair may bond to carbon plus charge. We can call this ionization. We can call this nucleophilic addition to the carbocation. We know in terms of stereochemistry, we attack either side of the carbocation, front or back. It's not really any stereochemistry shown anyway. How do we get final product from here? Something takes the H, we have Br minus floating around, it's still over here. Let's use it right here. These electrons take the H, leave electrons on the oxygen, we get that plus what? Plus HBr?
Would it ever be the case for the solvent to take the H?
It actually could because, I mean, this has the same basicity of water. How does HBr exist in water? H3O plus Br minus. Yeah, if you wanted to show ethanol taking it, you could do that also, and you would make ethanol protonated, and then you would just show the Br minus beside it. That's okay. Because again, if this was water, you have H2O in water, but how does HBr in water, how do they exist? Well, it exists as H3O and Br minus. That oxygen is, but as I've always done, I like to kind of reform the actual small molecule, make the line reaction balanced. How do we get the other product? What do we know about carbocations? Always prone to rearrangement. We have this tertiary carbon over here. If this H moves over, What does that give? It gives a tertiary carbocation by hydride shift, minus shift, carbocation rearrangement, skeletal rearrangement. Now how do you get final product on the right? Well, ethanol, these electrons could attack here. You give the same type of intermediate here, and then you lose proton to give that. Regiochemistry. The O-ethyl ends up in two different regions of the molecule. These are regioisomers. The only way you're going to get that is to have a cation that rearranged. Has to be SN1. If this was SN2, the nucleophile would only be right there. Comes in and kicks the leaving group off. Could this be SN2? What type of nucleophile does SN2 require? Strong. Is ethanol a strong nucleophile? Is it an anion? No. Is it an sp3 nitrogen? No. Ethanol is not a strong nucleophile. Ethanol cannot do SN2. At least not as an opening statement. Can you do SN2 on a secondary halide? You can. You would never do it on a tertiary halide, but you can do it on a secondary. Usually solvolysis reactions are SN1 because usually solvents are neutral and usually they're not sp3 nitrogens. Now consider stereochemistry in the above reaction. Show the products with stereochemistry. Same two products, but show the stereochemistry that you would get if you did this reaction. Now, I also gave you stereochemistry to begin with here. Where up there, I did not. It was just all, no stereochemical considerations up there. If you started with this, we would get this product here. What would the stereochemistry of this carbon be?
Coming out.
How would it be coming out, Dave?
Because of inversion. The stereochemistry.
No, we did SN1, right? We attacked carbocation. Right? It's the same exact mechanism, just having completing stereochemistry. We didn't do SN2 up there. We did SN1, right? SN1 doesn't have inversion. SN1, we attack cation. You attack this cation, or are you going to attack it from the front or back? Both. It's going to be racemic here. There'll be two products. For this, there'll be two stereoisomers for this regioisomer. What will be the relationship between the two stereoisomers of that regioisomer? Epimers? Yes. Because you would get what? You would get this being bold, this being bold. You would also get this being bold, and this being dashed, right? There would be no change here. Why would there be change there? There would not be. You would attack cation from the front or back. What's the relationship between these two? They're epimers or diastereomers. The whole molecule is not racemic, it's racemic right there, but this is defined stereochemistry because there was no change. Now if we had the other product, what would be the stereochemistry of that? What's the stereochemistry of this? There is none. That's not a chirocarbon. It's got two ethyls attached. Forget about it. There's no stereochemistry there, right? It's like me showing you one of those paper clips and saying, okay, what's the stereochemistry? Well, there ain't none. There's only one way to show the paper clip. Yes, it is tetrahedral. But it didn't matter what do you show forward or back. It's all the same thing. Your choice. So that's a good old example of an SN1 reaction, solvolysis reaction. Not all SN1s have to be solvolysis. Here we just reacted with ethanol, which is kind of a common solvent. There was no other reagent, so it's called a solvolysis. What's the rate equation for the above solvolysis reaction? Rate equals some type of constant. What else? Times concentration of what's the rate equation for the above reaction? What type of nucleophiles react strictly by SN1? Weak. Somebody said tertiary. I'm not sure what that means. What do you mean tertiary? Nucleophile, not electrophile. I mean, here's the ethanol was a nucleophile. It's not tertiary, but it is weak. What type of nucleophiles react strictly by SN2 mechanism? Strong. To do an SN2, you have to have strong nucleophile. But also, if you have strong nucleophile, you're going to be doing SN2. Because strong nucleophiles are bullies. They can't help but keep putting their nose in backside. Okay? See, up here, ethanol's weak. It's not going to stick its nose in backside. It's not strong enough to do that. So it just sits back and it's not going to do anything. It's too lazy to get off the sofa. So it's all up to this guy. And with a little heat, what does this guy do? It ionizes. You're not getting any help from the ethanol kicking that bromine off. Not in a rate determining step. So you're not doing SN2. Anybody figure out the rate equation?
Concentration of the reactants.
Which reactant?
Um,
Is it SN1 or SN2?
SN1.
That means there's one molecule involved in the rate determining step. Which one is it? Alkyl bromide. That's it. It's SN1. What is the rate determining step up here? I've already erased it, but what was the rate determining step up here? In the mechanism.
The formation of cation.
Ionization to make carbocation. Was ethanol involved with that? No. No. So if you change the concentration of ethanol, does it matter? No. So why would you put it in here and say it matters? I mean, if you put ethanol here and then you change it, then that's going to change this. But ethanol does not change the rate. Summing it all up. Substrates with leading groups on primary carbons only undergo SN2. That's because you would never do SN1 for a primary carbon, right? Because you would never make a carbocation on a primary carbon. Substrates with leaving groups on tertiary carbons only undergo SN1. That's because you would never do backside attack on a tertiary carbon. So you would never do SN2. Substrates with leaving groups on secondary carbons can undergo either. So if it's secondary, you're going to have to use other information to predict mechanism.
So in the primary and the tertiary carbon, it doesn't matter what the nucleophile is?
Well, I think I kind of get it down below. Let's look at this down below. I addressed that. It may matter. You may end up with a reaction that just will not occur. Because maybe it will only go SN2, but your nucleophile is weak. Sounds like you're not going to be doing a reaction. You know, if the substrate with the leaving group will only do an SN2, but you only throw a weak nucleophile on it, it sounds like it's not going to be reactive. With strong nucleophiles, reaction will always be bimolecular. That is either SN2 or E2. We haven't introduced yet, but bi meaning 2. Strong will always be bimolecular. With weak nucleophiles, which are lazy, reaction will be unimolecular, like SN1 or E1. As long as the substrate is secondary or tertiary. Because you would never do SN1 on a primary carbon. And in fact, you would never do E1 on a primary carbon. Both of those involve forming carbocations. If the substrate is primary, the reaction will have to be bimolecular. Because you would never make a carbocation on a primary carbon. And if you're just making carbocation, that's just ionization, and that's just going to be unimolecular. Of course, a bimolecular reaction with a weak nucleophile will be quite difficult, as what I just said to the question over there. Let's try some examples. What type of reaction mechanism will most likely occur with the following? Provide the product. If you take this benzylic bromide with that stereochemistry, heat it with water, what type of mechanism are we predicting? I heard SN1. Anybody else? Camille? SN1, why? Because it's a weak nucleophile. Weak. Lazy. SN1. The only thing that can happen here is this is going to ionize. Okay, show the product then, including stereochemistry. By the way, can you do SN1 on this type of carbon with a leaving group? No, it's not primary. It's secondary. Not only is it secondary, it's also going to be
Tertiary.
it's not going to be also tertiary. It's going to be secondary with resonance stabilization by the benzene ring. It's going to be a benzylic cation. Benzylic cations, they're also formed in mass spec, right? Product here, just going to draw this as phenyl. What's going to be on this carbon now? OH. What's the byproduct? Small molecule byproduct. HBr. That's where the other H ends up. We can envision a mechanism. What's the stereochemistry here? Racemic. Good, because the water attacks carbocation. The resonance stabilized carbocation. About the one on the right. Same electrophile. Now we're reacting with KOH. What's going to be the product? I'm sorry, first off, mechanism. This is minus, this is plus, yeah? Weak or strong? Strong nucleophile. SN1 or SN2? SN2. Strong nucleophiles are bullies. They're going to stick their nose in the backside. Show the product. This is not going to wait for this to ionize. Here I come, backside. What's the product?
OH going back.
It's the same connectivity, but here we have stereochemistry that's like this because SN2 comes with what? Inversion. Backside attack. What is this? Is that S? And that's R. Difference in nucleophile gave you two different outcomes. Do you want a racemic product or do you want an inverted product? What if you had this substrate and you wanted the S alcohol? Not a mixture of both, not just R. What if you wanted only S alcohol? Because the S alcohol could be sold for millions of dollars, and that's the one you wanted. How would you make it?
You use water.
Use water?
So that would be SN1 and you have
You would get both. Racemic means it'd be R and S. You'd have 50% S. What if you wanted it to be all S? How would you do it? You got this, and we want that. And we got this. How would you get that? 100%.
Maybe tosylate?
Tosylate is prepared from an alcohol. But I think you might be thinking of something. Anybody got it? Who wants to make millions of dollars? Let me show you how you do it. I'd react this with potassium iodide. React that with potassium iodide, what would you get?
You would get inversion with a good leaving group.
You would have this, which would be R. That's I minus, that's K plus. And at that point, you would then react this with what? KOH. And this would be another SN2. I would do two inversions. Because replacing this with I can be done. Inversion to R. But I is a good leading group. It's even better than bromine. Now you make your money. All S. Right? You need two inversions. How about if we take this alkyl iodide and heat it with methanol? What mechanism? Weak nucleophile. SN1. Too lazy to do anything. Just got to get this thing ionized. What's the product here? Show product. What you got?
Dash. OME.
What is the stereochemistry here? OME. O-methyl. That was a nucleophile, right? And then I minus took an H from the oxygen. Racemic, SN1. What type of product did we make here? Functional group.
An ester.
It's actually an ether. What is an ether, Alex? Okay. Product over here.
SN1.
I got an SN1. Connor, what you got? SN1? What you got, Mena?
SN1.
Everybody got the right answer?
No reaction.
No reaction.
Why?
I see a tertiary halide, tertiary leaving group. What type of nucleophile? Strong. What's it going to be? What did we say above? With strong nucleophiles, reaction will always be bimolecular. Tertiary, you can't do SN2. So what are we going to do here? It starts with an E.
Elimination.
E2.
Question.
This is going to be E2. This takes us into the next handout. Strong nucleophile, always bimolecular. They're bullies. They have to put their nose in. They have to be involved in the rate determining step. But you can't do SN2 because it's tertiary halide. So we're going to do E2. You can do E2 with a tertiary halide. Okay? Why is this not SN1? That's a great substrate for SN1.
That's a strong.
No, that's a bully. It's not going to sit back and let this guy just ionize. Here I come. So this is, you see how we assess this reaction? E2. We'll move into E2. In just a minute. Let's see. Provide reagents. Reagents. I'll let you do the first and third. Supply reagents for the middle one. What are we doing here? Looks like we're putting something on this oxygen. We're making the oxygen to carbon bond instead of OH. We're alkylating the oxygen. How do you want to do this?
Acetate.
Oh, acetate? Well, it wouldn't be acetate.
Use sodium hydroxide and take the H.
Sodium hydroxide to take the H.
Yeah, you
React this with sodium hydroxide, we're going to get this. Take the H of the carboxylic acid, make the anion plus water, you have this. Why did you want to make the anion?
To alkylate it.
What do you want to bring in now? Alkyl bromide with what? Alkyl bromide with that? With that? We want this here, yeah? What we have here is components of the product. What do we want to call this component? What was it in the reaction? I mean, it's right here. What is this?
That's an ester.
No, what general term is this component? Starts with an N. This is your nucleophile. This is the thing that replaces the leaving group. So instead of that there, we need an LG, and we need the nucleophile to replace the LG. Now, what type of mechanism are we going to do if we deprotonate this and make this an anion? If this is the nucleophile, what type of mechanism is it going to do? It's strong, SN2. So in terms of stereochemistry, it's going to give us inversion. So if we want this to be bolded like this with the over here, we want this to be dashed. So when this comes in here, kicks this off, you get inversion here, and we get that product. Because here it's R, but we want S. We need something to supply this alkyl group to put on the oxygen. We need an alkylating agent. An alkylating agent is an electrophile with a leaving group. Methyl iodide is a great alkylating agent because if you have this nucleophile, you'll put a methyl on your nitrogen. We want something on the oxygen. What do we want on the oxygen? We want all that. So we need all that with a leaving group. You need to think about it from kind of the opposite direction. What are we accomplishing here? How do you use these reactions? When you see a product, how could it have been formed? We're able to make an O-carbon bond because we can rationalize having a nucleophile reacting with a carbon with a leaving group. Something with a lone pair now bonded to a carbon because it displaced the leaving group that used to be on that carbon. The one at the top, please look at the note. You can do it two different ways. Please do that for next time. And the one at the bottom is a little bit bigger molecule, but that's okay. You can still see what's going on. This is lincomycin, an antibacterial agent that was discovered in the soil some microbes that grow in the soil. It was discovered in Nebraska. I'm not going to tell you what city in Nebraska it was discovered in. They later found if you convert the OH to a chlorine up here, this compound has better antibacterial properties, and they call this clindamycin. I'm not going to tell you why they begin it with a Cl. Clindamycin is used regularly in hospital settings today, usually as an injection, IV. You can look at propose a reagent that would do that conversion. Did anybody figure out where this was discovered? Lincoln, Nebraska? Yes. Okay. On the back, there's some for you to work on, ask questions about, including here or SI. These are also mechanisms. Actually, they are mechanisms, not predictive product. It's mechanisms. Okay? All mechanisms. Please be working on these. Let's move to E1, E2. By the way, let's look at the very last page of the handout. Please look at this. Here's an example of an SN2 reaction here. I say SN2 most likely. Read back. How to confirm? How would you confirm that it was SN2? And why does it matter? Please think about that. How would you confirm? That's the synthesis of Zyrtec. Anybody ever taken Zyrtec? Okay, elimination reactions. Now we did substitution. Now elimination reactions are actually the opposite of addition reactions. With alkenes, we did addition. If you take an alkene, react it with HBr, get this, we added HBr to the alkene. Addition. What if we come this way? The opposite. What if we take that and get this? What would we have to remove? We have to eliminate HBr. So we're doing the opposite of our old alkene reactions. But the reason it falls into here is because what type of substrate are we using? A tetrahedral carbon with a leaving group. Coming here, we don't substitute, we don't replace the Br with something, we eliminate HBr. Or we eliminate something else. The leaving group will still leave. Common for substitution elimination, leaving group leaves in all these reactions. For example, here's a synthesis of a compound, Tamiflu. Hopefully you don't have to take that this season. Right here, they do an E2 elimination. DBU is a base. THF is a solvent. What are they eliminating and going to here? The iodine is leaving. What else is leaving? There's two H's there. There's only one H there now. What did we lose? We're losing HI. We'll eliminate HI from that molecule, just like over here we eliminate HBr. Put in the double bond by an elimination of HI. Whatever we eliminate, this is what we formerly eliminated. This formula is missing HI. But we may not necessarily form HI. This is what we formerly eliminated based on formula. E1 and E2, the 1 and 2 means the same things as SN1, SN2. E1 is unimolecular, and E2 is bimolecular. E2, there's two things involved in the rate determining step. Same idea. Okay. General introduction again. Pretty much has already said this. What we're going to have is a carbon with a leaving group. Instead of a nucleophile, we're going to have what we call a base. But it also is going to have a lone pair. The reason we're going to call it a base is because it's going to abstract a hydrogen. The lone pair will act as a base. It will abstract a beta. Abstracts beta hydrogen. Of the terminology. We will be doing a beta elimination. Terminology that we will clarify. Take this, react to a base. We can get the alkene plus the leaving group. Probably going to be an anion, but it doesn't have to be. Now the base has the H. It's a very generic introduction. We've already kind of said all this stuff here. Same applies for substitution. Here's an exact example. We take one bromopropane, this bromo alkyl bromide, react it with this anion. We can get this alkene, Br minus, and now the base has the H. Just like with SN1, SN2, let's do two different mechanisms and then let's look and see which one we like the best. We're going to do both E1 and E2. E1. And I see that this has the same problem. I didn't update it last time. I probably updated it, but I didn't print it out. I copied the wrong one. This needs to be changed to E2. And this needs to be E1. Well, E2 is going to be our concerted mechanism, like SN2 is a concerted mechanism. I actually wanted to do E1 first, but it was easier to switch that instead of all that. Let's do E1 first. Okay. Leaving group's got to leave. Everybody agree? One thing that could happen is this thing could just ionize. Let's come down here. If it just ionized, that would give us that carbocation plus what? Br minus. Ionization. And I know some of you are already hating this mechanism. Right? But we're going to do it anyway, and we're going to then, okay? Ionization. We made Br minus. How can we get the alkene and also get the other product up there? Well, if you look at this, there's two H's here. Right? There's two H's there. Hold on, I'm listing. No, I haven't. 3 carbons, 3 carbons. It's just I don't have the extra bond there. 2 H's there or here, right? 2 H's there. 2 H's on the central carbon. How many H's on the central carbon now? Only 1. Something has to take this H. What could we show taking it? Well, this guy here looks like an H. These electrons take the H. Where would these 2 electrons go? Where could they go to get to where we need to go? These could just fall in here and make pi bond. Base takes H. Here's the H. Takes the H, these electrons just move in, make pi bond. What does all this give? Did we make everything over there? We made Br minus by ionization. We made the alcohol on the right here. And we made the alkene right there. All of our arrows are there. What will be the rate determining step in this mechanism? How many steps? 2 steps. What's the rate determining step? Ionization, just like for SN1, okay? Of the 2 reactants, which one or how many were involved in the rate determining step? Was the alkyl bromide involved? Of course it was. It's the one that ionized. Was the alkoxide involved? It had nothing to do with the ionization. So the rate is going to be some type of constant times what? Alkyl bromide times what? Anything else? That's it. So this is unimolecular or bimolecular? Uni. Did we do an elimination here? We did an elimination unimolecular, E1. Just like SN1, it will involve a carbocation. And formation of that will be rate determining step. This will be fast, removing the proton. If we did a reaction coordinate diagram, we would have how many intermediates? Just one, carbocation. Then we would go to the final product. We'd come right down here. What do you want to call, this is ionization, what do you want to call this step? We call this beta elimination. The whole process is sometimes called beta elimination, but what does beta elimination mean? We remove the beta hydrogen. Because the leaving group is said to be on the alpha carbon, the next the beta carbon. We removed a hydrogen from the beta carbon. That's just terminology. Extraction of the proton or the beta elimination, this is the fast step. Do you think this reaction is thermodynamically favored?
No.
2 sigma bonds, gone. We now have a pi bond instead. Is it thermodynamically favored? No. You're going from 2 strong sigma bonds to a pi bond. It's not thermodynamically favored. But it can be done. It's actually favored by entropy. Because we're eliminating something. It's just the opposite of this. This is favored by thermodynamics, but not entropy, because we're adding something. When you eliminate, it's like breaking it apart. That's favored entropically, but not thermodynamically, because we're making pi bond. Okay, that was E1. What's another way we could show this? E1, this is supposed to be E2, right? Another way we could show this is like this. Concerted. These electrons could take the H, these electrons could move down, and these could be kicked off. All together now. All that's concerted. What does all that arrow movement give? What does all this give right here? It gives that, right? Because right here, what is this arrow doing? Taking the H, that gives the final thing. What is this arrow doing? Bond's moving in to make pi bond. There it is. What is this arrow showing? Leaving group leaving, all at the same time. All concerted. No intermediate. And certainly no carbocation intermediate. Does SN2 have a carbocation intermediate? No. Neither does E2. It's an all concerted rate elimination. We're out of time. I want you to do this. There's another way to show this. I propose two mechanisms. Which one do you like better for this example? Do you like the primary cation? Oh, bad. This is an example of what? That's an example of an E2. That reaction is going to be E2. You don't make carbocations here, right? There's a third way to show this, a third mechanism we could propose. The third mechanism may not even be in your textbook in this chapter. It's probably later over. Somebody come up with another way that you could show this to make these three. I showed you two ways, and those are the two ways that we will discuss here, E1 and E2. But see if you can come up with a third way. And we'll be moving ahead. Lab this week is double E2 elimination of the bromide you made about 5 weeks ago. Those leaving groups, 2 leaving groups on that guy.